Hello all and welcome back. So in this video now, let us continue our discussion and found the space complexity of Fibonacci number, right? So again, this is some algorithm which we have done a lot in deep. We have drawn its recursion tree. We have found the time complexity. Now let us talk about the space complexity of this particular algorithm, right? So let me first write down the code. Fibonacci series, we used to write the code something like this. So def fib, let's say nth number. If it's less than or equal to 1, we used to return 1. Else fib of n minus 1 plus fib of n minus 2. Now here again everyone, if you will see, we are not creating any variable as such, like not a single variable at all, and no particular, I would say this thing, any array or any list, we are not creating rather anything. We are just making the function calls, and if the base case is there, then we are just returning, right? So now how will you are going to calculate this? So let us employ one thing again. So if you will see, this is the major thing, right, which is kind of a case which is going to get called. To understand how we are going to find, let us make the recursion tree again. We will be getting our n here, okay? Now one thing to understand here, if we understand the whole recursive relation, the one which you have written, first the whole n minus 1th tree is going to get called, right? So first this particular tree is going to get executed, basically this particular half of tree, this one. Once we complete this tree, then is when we are going to move to the n minus 2th tree, right? So we are not going to make them all together, no. First we know that this whole part of my tree is going to give me the answer, and then I'm going to make the call here, right? This is something which we have seen in recursion very closely, that first where you are making the call based on your recursive relation, the number of the function call sequence, right? I showed you how this is going to be the first call, this is going to be the first, then this is going to be the second, then third, then this will come back. So something like this used to happen, right? In a very similar manner, we are just going to make these calls, and when this left subtree gets the answer, then we are going to move to the next part, right? Now one thing to always remember, we are not going to make the calls simultaneously, or n minus 1 and n minus 2. Let us see the example for this. Let's say maybe with the 4. So for 4 now it's going to make the call to 3, then 2, then 1, right? Now if you remember, if you understand and see one thing, this is the maximum number of functions call which are there in my memory at a point, right? Once this gets done, I'm going to make to 0. Okay, so there are 4 calls. Now when this returns, I'm going to make this call, and here you will see just 3 calls are there in my particular function in a particular time, right? So on that note, this is going to return, and finally I'm going to make the call to 2. Then this 2 is going to make the call to 1, right? This is also 3 calls at a time. Then it's going to make the call to 0. This is going to return. Again, here also we have the 3 calls at a space, and then this is going to return, and finally we'll return our answer. So the point which I want to actually show you is that in this tree, at a point, the maximum calls are this green one, right? Maximum number of calls in memory. So it is this green one. If now I say that, okay, each function is taking some k space, then I can very comfortably say, because these are n calls, you will see that, okay, it is going till n, the space complexity is going to be nk, okay? So that's how we calculate it. Now let me show you this again using Python tutor, so that you are able to understand. Let's say now fib, let's say fib n plus 1, n minus 1 plus fib of n minus 2. So here again, what I want you all to focus on is that how many calls are in the memory. The maximum functions are in the memory. My bad, this is now changed to Fibonicci. Great. So pay attention everyone. Now I make this and make the call Fibonacci of 4. Then I'm going to make the call to this left, right? Just first I'm going to make this call. I'm not going to make the call to 2. I'm going to make the call to 3. Now this 3 is going to make the call to 2, and now it's going to make the call to 1. At this particular point, I have 4 functions in the memory, and if each is taking, let's say, case space, then I can very surely say that, okay, hey, my space would have increased something like this: one function, two function, three function, and finally four functions, right? So this is something which is the maximum as of now. Let us see what else is going to happen. Then I move forward, I get the answer. So this is actually out. Okay, so when I repeat this, return this, the second Fibonacci call get the answer of this particular call, and it's now gonna make the call to 0. When we make the call to 0, again, there are 4 functions in the memory, right? So this is kind of tamed. But now you will see that calls are gonna get reduced. So once it returns 0, okay, now I have 3 functions. With 3 functions, this is going to reduce. This whole thing is going to reduce. Okay. Then again, I have 3 functions, so it's going to be the same only. Once it returns, I have 2 functions now. So I think you can imagine now, right? So it's going to be the same. Then it's going to be for 2. Then 2 will only be there, then return. So something like this is going to happen. But the point which I want to make is that at one single point, now you see that there are 3 functions. So maybe this will jump. But the overall idea is that never will I go above 4 functions at a single time. So this is what I was saying, that we have to always see the peak memory, because yes, you might be making somewhere around 2 to the power n calls, but that doesn't mean that all of them are taking your space all at once. No, one function gets created and then gets destroyed. So the space is freed up. Okay, so again, that is very important to understand. I will repeat what I just said. When a function is created and destroyed, the space overall is freed up. It's the same as, let's say, in your pen drive, you copied something and then you just deleted it. So the space is freed up. You cannot say that, okay, this is still taking up the memory. Okay, you will be actually considering the memory when everything is there. What's the maximum memory which reached, right? That is the overall space complexity of the anything which you're doing. Okay, so because each and every of these functions, when they get deleted from the scope, the space is freed up, I will just be seeing the peak memory which is used. Okay, and this thing is very, very important to understand, everyone, as well as to explain something which not all students are aware of. Okay, so please make sure that you're able to understand this. And once I actually now continue my whole work, never will you have 4 functions now. That is the whole understanding. See, 3 are there, again 3 are there, then 2 are there, and finally I get my answer. So this is the point which I want to explain you with respect to this recursive relation and call. Now again, the understanding here is that you should be very much comfortable in recursive, making the recursion call, as well as, second, okay, I think it's called on it. Yeah, cool. So I will draw the memory here as well. So you should be very much comfortable, and that's the reason I was always pushing you to write the recurrence relation, right? Always I was pushing you to write the recurrence relation, because we are going to get graph something like this. Then it's going to increase, then going to increase, going to stay the same, then 3, then maybe 2, then again 3, something like that. Of course, you can make it, should be fine. Okay. Again, I'm not drawing it perfectly, but I hope I get the idea across, and I am majorly interested in this memory. Okay. So yeah, that's the overall way we find out. So let me write down the answer finally. Space complexity is big O of n, because it will be nk. Nk I can always write less than k plus 1 n. And now you know the whole drill. This is going to be my g of n. If this is my g of n, then I know my space complexity is O of g of n. So everything, if you will see, is getting connected to the introduction which I gave, right? So that's the reason, if you understand with this flow, right, your understanding is going to be actually unmatched. Cool. I hope this was clear, everyone. Again, this is a little tricky. We'll request you to see this once again if it is not clear. Should be have shown you using the visualization as well. So please make sure that you actually understand this and employ this when you are finding the complexity for recursive calls. For iteration, again, this should be easy. Okay. So yeah, let's meet in the next video, and we will see what else we can understand about space complexity. Thank you.